It's an honor to be here today at the High Performance Software Foundation conference to talk about the work of my team on the GPU porting of the Trust platform with Kokkos. So I just arrived in the Trust team, so I'm mostly going to be talking about other people's work, but I was still chosen to talk here. So I work at CEA, the French Atomic Energy Commission. So the summary for today, I'm going to start with an overview of the Trust platform. I will then explain our GPU porting strategy and in particular why we chose Kokkos. I will present the GPU performances we obtain with Kokkos, the lesson we learned along the way, and the future work and conclusions. So what is the Trust platform? It's a fluid mechanics, thermohydraulics simulation code which handle incompressible and weakly-compressible flows, single and multi-phases flow, and also has a front tracking modules. It's massively parallel, thanks to MPI, and was scaled to 50,000 CPU procs before. It supports 12 research and industrial applications of different scales, including purely CPU ones. So it's also important for us to keep the good CPU performances because many codes are based on Trust. It is a demonstrator for the CExA project, which is the internal CEA project for helping porting legacy code to the exascale. It's written in C++ with 300,000 lines of code. It's open source on GitHub, and we identified 1,400 kernels to be ported to the GPU. So it was started in 1994 and is modernized regularly with a growing team of now 10 people. So some simulation example, I won't go into the details, but on the left we have a pressure water reactor, then we have a vortex agitator simulation and a fuel cell simulation. So various types of things we can do with Trust. So what's our porting strategy for a large legacy code? So the way we proceeded is that we ported to GPU the most expensive parts of Trust. So that's a flowchart for a Trust simulation. We start by reading the input. We then compute the operators and the model. So usually it will be the Navier-Stokes equation on a given discretization. We then assemble a linear system of equations that we solve thanks to an external library. We write the output. If we converge, we stop the simulation. And if we didn't converge yet, we go back to computing the operator and model on the updated data. And so if we measure the runtime, we can look that we spend 70% solving the linear system and 30% of the time computing operators and model. So the first thing that was ported to GPU was the resolution of the linear system using external GPU-enabled linear algebra libraries. So we use AMGX, PETC, Hyper. So Hyper is through PETC, and Rockalution for AMD GPUs. That was the first part. And then the second part was to port to the GPU our computing of the operators and model. So this is kernels that were already present in Trust that we ported to the GPU thanks to Kokkos. So why Kokkos? It's quite a long story. So the GPU porting of Trust, the first experiment started in 2014 using the first GPU-enabled libraries of PETC for solving the linear system. In 2020, some tests were done with the Nvidia AMGX library. In 2021, the first Trust kernels were ported to the GPU using OpenACC during an Nvidia hackathon. In 2022, there was a partial port to AMD GPUs with OpenMP targets. And then in 2023, Kokkos was selected as the portability layer through the CExA project. And then in 2024, all the OpenMP target kernels were ported to Kokkos. And so the reason why we chose Kokkos over the two other programming model is that, first of all, there is more support locally in CEA thanks to the CExA project, but also it gives us portability to all the different architectures and also native multi-dimensional views and kernels. So what feature do we use in Trust? So at the center of Trust, we have an array container called the Trust array, which has two main things. It has on the CPU side a std vector that contains the data on the CPU, and on the GPU side an unmanaged Kokkos view on the GPU. So unmanaged means that we still manually allocate and deallocate the memory of our view, and So device memory is still allocated and destroyed with Kokkos malloc and Kokkos free, but that's an artifact from the OpenMP target era of the code, because when you do OpenMP target, you have to manually allocate and allocate. So that's that's an artifact that we will get rid of, and eventually we'll reuse fully managed views. We use Kokkos parallel for and parallel reduce throughout our simulation, and we run on several execution spaces, so CUDA and HIP for our GPU application, and Serial for our CPU applications. So, as I said, we are porting the code progressively. We have thousands of kernels, and so the porting is progressive. So as we are porting the code, we need to have a hybrid code that runs CPU and GPU kernels after each other, but still giving us correct result. Although the full performance is, of course, obtained only when most of the kernels are ported to the GPU. So we need to synchronize device and host memory. To do so, we do explicit synchronization from host to device before each kernel. So before a kernel, a GPU kernel, Kokkos kernel, I call the accessor that we wrote, so we wrote several accessors, so view read-only, view write-only, and view read-write. And so right before a kernel, I call these accessors, and if necessary, they will perform a host-to-device synchronization. For device-to-host synchronization, it's slightly different. We do it implicitly. So essentially, we rewrote the access operator of our trust array by adding this function, the ensure data on a host. And this function detects if the data is more up-to-date on the device, so out-of-date on the host. And if it is the case, we do this synchronization from device to host. So that is quite expensive, because now every time we access a trust array, we do this check. But it's a safe, necessary choice for several reasons. First, most of the thousands kernels are not ported yet. So when I port a kernel to GPU, it's hard to detect what CPU kernels or even just simple CPU operation I'm going to go through after my GPU kernel. And it can take days to detect this kind of stuff. And also, many people who are writing on top of trust are not GPU-aware people, and so we cannot expect them to think about adding this synchronization all the time. So for now, it's kind of our necessary safe choice. We also use dynamic kernels, so credits to Paul Zener from the CExA team for this structure. So the idea is, especially for small kernels, we want to limit the amount of host-to-device transfer. So we wrote kernels that dynamically choose between the host and the device execution spaces at runtime based on the availability of the data. So essentially, we wrap our kernel by the execution space. We template the kernel by the execution space. So we have a device version and a host version. And before some of these kernels, we check where is the data. Check data on device is going to tell me if my CPU STD vector or my GPU Kokkos view, which one is the most up to date. And based on that decision, on that information, I will make a decision on where I run my kernel. So what's the state of the porting? So as I said, 300,000 lines of code and more than 1,000 loops. The porting started during the Gen C project in 2022, and in 3 years, 5% of the kernels were ported to the GPU. And then it stagnated until 2024, when the CExA project started, and it took off with the CExA project, and now we are around 14% of the trust kernels that are ported to the GPU. And we estimate that by the end of 2026, we should reach 50%. So there is a big acceleration since we moved to Kokkos. So now the performances, what did we get? So let's consider a rather simple simulation. So we have an injection of a turbulent jet of hot water into cold water at Reynolds 3000. It's a LES calculation with Boussinesq hypothesis and semi-implicit scheme on 2.5 million meshes, elements. And we compare the performances of trust on GPU nodes, V100, A100, and H100, versus CPU nodes. And it's important to note that most of the kernels of this simulation were ported to the GPU, as you can see in this chart here. And so compared to the AMD Milan node, you can see that we have a speedup of 2.5 on V100 or 100, 4.3 on A100, and 6.7 on H100. And so our goal and our typical speedup that we aim for is a factor of 4, so from from 3 to 4.5 when we port a simulation on the GPU. So let's look at weak scaling. So here I increase the size of my problem as I increase the amount of GPU or CPU I give to the problem. So I go from half a node to 256 node, and I do this for CPU and GPU. So CPU in blue and GPU in green. We can see that for half a node we have quite a good speed up of 3.6. But as we increase to the full machine, the full industrial machine in this case, the speed up is degraded. So the CPU computation scales well, but the GPU computation does not scale so well. And according to our measure, the slowdown is mainly caused by the GPU-enabled algebraic multigrid libraries that we use. So they seem to not scale so well. Another example, after weak scaling, we look at strong scaling. So I keep my program size fixed, and I just throw more GPUs at it. So here in this chart, we have the time spent on 32 A100, 64, and 128 A100. And if we look at the details, so in yellow we have the time spent in the communications. In orange we have the Kokkos kernels. So these are not Kokkos kernels; these are trust kernels that we ported to Kokkos. So I should have changed that. Yeah, we don't use Kokkos kernel yet. And in blue we have the time spent in the linear solvers, right? So as you can see, from far away, it seems that the trust kernel that we ported to Kokkos scale well as you increase the amount of computing power, but the linear solver do not scale linearly with the amount of GPUs that you throw at it. So it seems that we have some issues with the AMG libraries that we use, so AMGX and Hyper via PETSI for now, with a degraded speed up between CPU and GPU. And so for us, because on the CPU it scales well, so you only have a handful of AMG algorithm that you can run on the GPU. And what we observe is that they seem to have a lower convergence rate than the CPU one. So it's not that the iterations are slow or not well programmed, it's that the overall algorithm seems to have less good convergence property. Also, we activated GPU-aware MPI in Trust, which helped us with performances, but it does not seem to help AMGX and Hyper linear solvers. And it's also, well, it's a well-known problem, but it can be tricky to fine-tune the AMG parameters for each simulation, because optimal choice may change with the type of GPU card you use, the amount of MPI process, your physical parameters, and your numerical parameters, of course. So it's something that's tricky for us. So what lesson did we learn during our porting? It was very helpful to have a modular C++ code, of course, to enable an incremental port. It was helpful to rewrite code, so template to factorize operation before porting. It's important for us to keep performance testing on all backends, and that should be included in your continuous integration workflow, because as you make GPU optimization, you need to make sure that you don't ruin your CPU performances. It's good also to use dedicated GPU libraries for performances, so for math and for communication. In general, performance is quite tricky to reach. I think everyone is aware here, but you have to focus on heavy computation because GPU efficiency increases with load. You can see here that it's only useful you use your GPU more and more as you throw more degrees of freedom at it, and it's only useful to use two GPU after a certain size. All the heavy loop of a trust simulation must be ported to get good performances for several reasons, because a heavy loop not ported to GPU dramatically slows down the simulation with 4 overhead. So you have the expensive synchronization detection for array, our inline operator that's not our access operator that's not inline anymore. You have a expensive device to host copy before the loop, an expensive host to device copy after the loop, and also there are fewer CPU cores on a GPU node than on a CPU node, of course. So when you run a CPU kernel on a GPU node, it will take time. So for us, 95% activity rate on the GPU is the main goal for each simulation. So yeah, port all kernel of a simulation and then optimize them It's only when you have everything that's ported that you want to fine-tune. Reduce high bandwidth memory access as much as possible. Make them as coalescent as you can. It was good for us to exploit parallelism with MD range policy, but we did observe some weird behavior. For instance, if I do a MD range policy with n that's a large dimension and dim a number of dimensions, so n is going to be the order of magnitude of millions, right? Dim is going to be 1, 2, 3. We saw great speed up for 2 and 3, but slow down for dimension of 1 in our specific kernels. So you have to be careful of that. We also saw some. Saw some slowdown of range policy in the serial backend versus like a standard serial loop. So you have to be careful if the performance is sensitive here, and report to the Kokkos team, which was reactive in our case and solved the issue that we mentioned. So don't stay in your corner. Talk to the Kokkos team, right? And some features for us seems to not be worth anymore. So it used to be beneficial to have random access memory traits. But for instance, since V100 architecture, it seems that non-coalesced read operations are more efficient since to L1 cache improvement. So I wonder, maybe we can talk about this later. Have you noticed this too? For us, it's you lose a lot of performance if you do non-coalesced write operation, but nowadays not so much if you do non-coalesced read operation. That's kind of what we observe weirdly. Also, the atomics operation performance have improved. So future work and conclusion. Are we going to enable Kokkos for all trust-based apps? So as I said, trust is used as a base for several applications with simulation time ranging from minutes to days and discretization number ranging from 1,000 elements to billion elements. Of course, the answer is no. Not all of our applications are going to be ported to GPU. We observe a tipping point between 100,000 cells and a million of cells. On the left of that tipping point, it's useless to do GPU. But even for the purely CPU application, Kokkos may still help to exploit parallelism with CMD and OpenMP. So Kokkos may be useful in this whole range. We would like to evaluate asynchronism, for instance, with a Kokkos partition space. So it would be nice to see if we can launch kernels asynchronously to keep the GPU busy for smaller problems. So essentially, shifting the CPU to GPU jump, try to shift it as much as we can to the left. For instance, by applying boundary condition in parallel instead of sequentially, or computing equation term asynchronously instead of sequentially. We also are working on the layout. So this is a kind of an unclear subject for us at the moment. But for now, you are using a layout right representation of the data on the CPU and on the GPU. So the default choice of the Kokkos view is layout left on the GPU, but we force the layout right. Again, that's a reminder of the OpenMP target directive. And the transpose, doing the transpose is quite an amount of work, so we have not completed yet. But the idea would be to introduce layout left on GPU and layout right on GPU, and layout right on CPU, sorry, and transpose every time we do a host-to-device copy. But we still have to investigate this. For the trust kernels that we ported to Kokkos, we would like to use hierarchical parallelism. We are starting to experiment with that with the CExA team. With this, using the scratch memory. And it would be nice also to try to use the Kokkos kernels instead of porting the math trust kernels, because in trust, we implemented a low-level vector addition, difference, element-wise multiplication, all these standard operations that are in a Kokkos kernel, and it would be nice to leverage Kokkos kernel here. For linear solvers, it would be also nice to use the Muelu AMG library and see if we get better performances than with the one we've tried so far, and also evaluate the Kokkos support inside the PETC library. So, yeah, that's it for me. Does anyone have any question?
All right. Over there, Mark.
Hi. Yeah, great talk. Thank you. I do have a question. Since you instrument host-to-device copies with function calls, does that help you diagnose
Yeah, so when you launch a trust simulation on the GPU, at the end, you can generate a report saying you did 100 hosted device copies. So we keep track of this. That helps us.
And also, have you tried using managed allocations? Does that have a, how is the performance impact of that?
You mean manage for the Kokkos view? When I mention unmanaged Kokkos views versus?
No, it's different. It's shared space.
No, we haven't tried this so far.
Okay. Try it out.
Yeah. Okay. I'll keep that in mind.
Have you tried looking into dual view, since you're kind of like replicating that behavior?
So the funny thing is, since we started I wasn't there. Since I was doing my PhD, when they did the OpenMP target polling, they kind of reinvented the dual view, right? With the my data is up to date on the view or on the device, on the host or on the device. It could be replaceable by dual view, but it wasn't done, and I think we were kind of discouraged to use dual views.
Which means we implemented the whole. Can you go back to your serial performance thing?
Serial here?
No, go back. What did you mean when you said atomic simple?
Because a lot of our kernels are still using atomics.
But you're referring to this when you use a serial backend, or you?
No, this is on GPU. Yeah, atomics on the CPU is
okay.
Not atomics, right? But yeah, we mean on the GPU side.
All right, I think we are out of time. Let's thank Rémi again.